The second thing is that actually this algorithm should not bring the right answer. I feel this is like cheating using this algorithm. Because if it would be random test data, it would not work like this.
Good morning, everybody. Welcome to Advent of Code Day 8. I'm Thomas, and my guests today are Frank. Good morning, Frank.
Hello, Thomas.
And Achim. Hi, Achim.
Good morning, Thomas. Good morning, Frank. Hello, world.
So, who of you will introduce us the riddle for today?
Today we are in the haunted wasteland, so we need to escape from some kind of sandstorm. And we are given some kind of map. This contains of movement directions. So at the first corner, move right. At the second corner, move left, and so on and so forth. If we come to the end of this move order, we start from the beginning. It cycles around. And we are given a number of nodes. We're starting at node AAA, and we have to get to node ZZZ. And for this example, as you can see, if you are at node ZZZ, you stay at ZZZ. So we need to go through that. And we also have a second example with more movement orders, but less nodes. And to do that, I can go to the code for part 1. As usually, we have to pass the nodes. Note here the use of the skip method on the stream, so I skip the first 2 lines. And the first one I just put into a string with my move orders. And then I start at node AAA. I have them in a hash map. And I move forward until I am at move ZZZ. And depending on the move orders, I take the left node or the right node. Pretty easy. Count up the steps. And the index on the move order, because it wraps around, I increment it and do a modulo against its length.
Okay,
so,
why is a modulo needed?
For the example, I am given a move order of 2 steps. But I probably would need to take more steps.
Okay.
So I need to do right, left, right, left, right, left, right, left, right, left, right, left.
Yes.
It's a repeating pattern.
Yeah.
And that's why if I have my move orders has a length of 2, and I need to do the third step at index 2, I need to do the modulo by 2 to do this to do step 0 again.
Now I got it. To repeat every time again, right, left, right, left. Okay, now
Exactly.
I got it. Yeah. Okay.
That was pretty easy. Part 2.
Well, one second, Achim. Some comments from Frank to this? Is it you have solved it in Rust, right?
Yes, in Rust, but it's basically the same. So you see here, you got this loop until you find end node and you simply count the steps. So it's not too complicated.
Not too complicated. Okay. Then what about part 2? Frank, can you explain us part 2 of this riddle, please?
Yes, I will try to do so. So in part 2, we have the same input, the same path with this left and right, and the same nodes in our graph with always 2 edges, one left one and a right one. So now in second part, we do not start at node AAA, but instead we start simultaneously in all nodes that end with an A. In this example, it's the 11A and the 22A. And now the question is, if we step according to this path, then at which step are we with all of these nodes on a node that ends with a Z? So here it would be probably this 11 Z or the 22 Z, or one of them. So this makes it really long, this example here. The solution is really long. We need to step very, very long. In the first part, it was about 20,000 steps, so it runs pretty fast. But in the second part, if you think about it, it can be a lot of steps. You see here, my puzzle answer was several billions. So we need to find a way to do this somewhat faster. And now if you think about it, how such a path looks like, if we start at 11A, then at some point we are at a vertex with a Z in the end, and then at some point we again get a vertex with a Z in the end. And actually at some point this path loops around. We will end up at a node where we were before, and then the same path again applies, and then this loops kindly like forever. And this happens for each of these nodes with an A in the end. They loop forever. And in these loops, at a certain point of steps, we always step on a Z node. So we have to combine these numbers of steps to each other. And now this looks a bit like a path, linear path, and then a loop in the end. And this loop goes always around. And now it turns out the data is organized in a way that we can ignore most of these facts, and we simply have to count the steps for each of these A nodes until the first Z node is found. And then from these number of steps, if we combine them, in my example or my input data, it's only 6 A nodes and 6 Z nodes, then we can use the greatest common divisor and the lowest common multiple to calculate the number of steps we need to actually come with all nodes to a Z node.
Okay. So I'm interested in your code, and then after that, Achim is back. I'm interested also in Achim's code. So I want to have today both codes, Rust code and Java code.
Yeah, then let me show quickly that the Rust code in this case. So first, what we need is an GCD and an LCM. Unfortunately, in Rust, in the current version of the libraries, there's no GCD like there is in C++, for example, or also in Java. There's a GCD available, but I had to Google it and copy it down. It looks like this. I guess it's the algorithm of Euclid, also known. You learn this in 5th or 6th grade in school and then quickly forget it. So 50 years later, you have to remember. And the LCM is an application of the GCD. It looks like this. You calculate the GCD, and then with this formula, you get the lowest common multiple of two numbers. So what we do now in our code is we find all nodes that end in an A. I collect them here in a vector called nodes A, and then I run for all of these nodes A, the loop, until I find a Z node and count the steps simply. And then these number of steps I put into another vector, which I called V. And then in the end, I calculate from this vector of V numbers, it's 6 numbers in my case, the lowest common multiple of these 6 numbers, and that's the answer of the riddle.
Okay.
It's actually, it's funny thing with this riddle is that a simple algorithm only works because the test data is organized in a way that it works. Actually, it should not work so simple. The problem itself is much more complicated, but it's the gag of this riddle that he organized the input data in a way that this simple thing works.
Cool. Yeah, Achim, welcome back. Can you show us the solution in Java? Frank explained it very well, and now for your solution.
Yes, for the solution in Java, I put that down into a different class. So I determine the start nodes, as Frank explained, those where the last character is an A. And for each node, I try to find the loop that I probably have. So the idea is, if I go through the nodes using the movement orders, I would come to some node that ends with a Z, an end node, but from then on I could move further on and would then move into some kind of loop. And I have to synchronize the 6 loops that I have because the data offers me 6 start nodes. So I have 6 loops. So that I reach for each loop an end node at the same time. That is a question that needs to be answered. So I process from a start point through the movement orders, and I note down every node that I visited, but not just the node name. I augment it with, where is it? Here. I augment it with the index of the current move order. So in the end, I will find a node with a movement order that I've already visited, because from then on, I exactly knew what will happen next.
This is for identify the loops.
Exactly. So the point is that node that breaks this loop, this one, which is the first point at which I am in the loop, has some kind of ramping up phase, some kind of initialization. So some nodes that I will never visit again, at least not with those movement orders. And anything else beyond that will repeat infinitely, so that I can then calculate a point in time where I am on all 6 loops at a terminating point.
Okay, cool. What was
that is the idea. I have here debug output. This is a name of the starting node. This is the length of the initialization phase. This is the length of the this is the number of nodes that I have to visit to find the loop. So the total number of nodes relevant for that loop. And this is the number of nodes. Wait, that is the index of the node where I find the end node. And the interesting point is the last column and this column, when I add it up, I get this again. So there's so it's probably that that the ramp up phase is not that relevant, because we get there, and because in numeric terms it evens out. And that's why I can then go through all my indices, these ones, where I find the terminating node, and calculate the least common multiple of these. And for doing that, I use the snippet that I found on Bildung. So if anyone would ask me how to do a least common multiple in Java, I will probably answer from now on. Well, there's a 3-line snippet on Beldum. Use that.
Okay, to recapitulate in my words, for every starting point, you have to find how many. You have to count the ways, and for all ways, you have to find the lowest common multiplier.
Yes.
The test data is organized in a way that this actually works. It's the gag of the puzzle.
Okay, nice.
If it wouldn't work, you would probably need to look into the Chinese remainder theorem, which is a lot more difficult.
Okay. What was the biggest challenge for you, Frank, for this riddle?
Actually, I had the right idea, but I had it because I did not understand the puzzle, but I wanted to do the LCM in first place and pretty early in the race. And then I was not able to write down the LCM function correctly. This was a bit annoying afterwards, but that's how it works. And then, yeah, the second thing is that actually this algorithm should not bring the right answer. I feel this is like cheating using this algorithm, because if it would be random test data, it would not work like this. That was difficult for me to understand.
And Achim, for you, what was the biggest challenge this day?
I didn't actually knew that Java has an own implementation of GCD. And as such, tried to implement LCM based on prime factors, and somehow did that wrong. So, guys, if you want to do LCM in Java, just use this.
Okay. What have we learned today? There are a lot of methods and functions implemented by Java, and we can use it, but not every function. LCM has to be implemented on our own. Nice.
Yes, and you need to have an idea where you would find it.
Yeah. Then, big thank you to you both. Have a nice weekend, and we see us tomorrow morning. Maybe.
Maybe.
Bye.
Goodbye.
Bye.